All right, lastly, before we get our nice long break, we'll go through kernel memory, which is treated different than user memory. All right, think about this. Why is the kernel, when the kernel needs memory, why are we treating that differently than user memory? This is kind of a tough question. Why is kernel memory treated differently from user memory? So there's multiple things going on here. First off, how many user memory spaces are there going to be? More than one. But how many kernel memory spaces are there? Just one. All right, so that's the first thing. There's only one kernel memory space. So is virtual memory really needed? Not really, no. But more importantly, why is virtual memory not used? Well, who services the virtual memory? The kernel. So that's a chicken and egg problem. You can't, if the kernel's trying to service the virtual memory, but you're trying to write the kernel to use the virtual memory, you can't be doing it that way. So we need to have something very special for the kernel to actually allocate memory for itself. So it's not going to be using virtual memory, it's actually using the true physical addresses because it's the kernel. And now what's the kernel? Now what's the kernel memory pattern going to be like? Well, let's think about the kernel. A kernel needs to be very small and needs to only allocate a very small piece of memory, hopefully. Some memory, kernel memory, needs to be contiguous. All right. We want this to be simple and fast because it's the kernel. We don't want to be using a ton of any complicated structures because usually the kernel jumps in, does what it needs to do, and needs to get out ASAP. So the first one, there's two systems used. One's the buddy system. This is an old version of memory for kernel. And then next comes the slab, which is what pretty much any modern operating system uses. So we'll start with the buddy system. Allocates memory from fixed size segments consisting of physically contiguous pages. Memory allocated using the powers of 2. This makes a lot more sense when you have a picture. Let's say you had only 256 kilobytes of memory. This was true at one point in time. And the kernel requests 21 kilobytes of RAM. Well, can we divide 256 to 128? Yep, that's still less or greater than. We can divide again to 64, that's still greater than 21. Divide again to 32, that's still greater than 21. We divide 32 again, you have 16, and that's less than 21. So then we're going to go ahead and allocate this whole block for the kernel. What's an issue with this allocator? I asked for 21 kilobytes of memory, it gave me 32. Starts with an F. Matt? You could use other words.
Fragmentation.
Fragmentation, right. Now we have holes in memory. Because we requested 21, and we got 32. That's 11 kilobytes of memory that's just unused. It's a hole. Not very most efficient use of memory. But this definitely worked. And we'll at least divide it up somewhat for you. Really, you're just guaranteed never to use more than twice the amount of memory you needed. And the algorithm's simple. So this actually was used for a long time because it's simple, it's fast. Nowadays, we use something called the slab allocator, alternate strategy. Slab is one or more physically contiguous pages. So we're getting pages back into this. A cache consists of one or more slabs. Single cache for each unique kernel data structure. So there's going to be a slab for each data structure. So you can tell the memory system that your data structure is this size, and it's going to have a cache of X number of those kernel objects. When a cache is created, fill the objects marked as free. All right. think the picture is going to help here again. Notice with the slab, you have to tell it how large your objects are. So on the left, the first slab is going to be contained of objects that have 3 kilobytes in length, and then you'll have different caches telling you where they are and different slabs. The next slab might be of 7 kilobyte objects, and you can tell you where those slabs are in memory. The point here is now you have to keep track of the size of your objects internally in the slab, and then it can actually allocate the memory more efficiently. All right, any questions? Doing great. Yeah, just trying to get through this because I will not be here Tuesday. Pre-paging. So some people wanted to go ahead and try and reduce the number of page faults that occur during process startup. So we all do something called pre-paging, because everyone uses demand paging. Pre-page all or some of the pages a process will need before they're referenced. So assume S pages are pre-paged and A is used. The idea is that if you can bring in a large section of all the pages at first, that should save you some time. All right, lastly, what's some issue with the pages? There might be some fragmentation. If the whole page is not used, you have holes. How big should the table be? If it's too big, you don't want to consume too much memory with your table size. That's not very good use. I/O overhead. You want to minimize the amount of I/O overhead per pages, so you probably want your pages to match what can be read from the hard drive. And you want to try and take into consideration locality where with your pages, try and bring in maybe the next page or reference is going to spill between pages as well. You do have to keep another issue. You have to keep track of this something called TLB reach, which means that the TLB could be reaching into a page table or page size that you did not mean to cache. So you need to come up with ways to invalidate the page or the entry in the table, but you also need to, so one thing you could also do to make sure you're not invalidating the TLB all the time is increase the page size, although this will increase the fragmentation, or provide multiple page sizes, and that will give you a little more opportunity, but then the TLB might have a hard time handling them. Okay, program structure. This is a great example. You have an integer array 1024 by 1024. Each row is stored in one page. So here, notice that it's, let's see what we're doing, J and I, and then we're going through the different columns, which means every memory reference is a page fault. While on the other hand, if we go through the entire column of the row, before jumping to the next one, there's only 128 page faults. So this similar issue with caches can also happen with page faults. Something called I/O interlock. If a page or memory is being locked because it's waiting for I/O to write to it so that the memory, so a process can read from it afterwards, you actually need to lock the two pages. For example, if these two pages are where a buffer is about ready to be written to, the operating system needs to lock these pages and make sure that they cannot be replaced, because we need to wait for the I/O to complete. That's just an issue you got to keep in the back of your mind. And yeah, Windows XP does this, Solaris. Oh my goodness. Yeah, so XP does demand paging. It does, like I said, have a working set minimum and maximum. All right, and that's what's used to try and automatically trim thrashing. And what does Solaris do? It maintains a free pages, amount of memory to begin paging, desk free to increase and begin swap. So it has a mechanism to change the page size to try and account for thrashing and different problems. All right, that's fine. Okay, that's it for chapter 9. Don't need to know too much about XP and Solaris, as much as the concepts here. Any questions on chapter 9?